Kyratsis is a professor in Department of Product and System Design Engineering, University of Western Macedonia, Greece. He is the director of the Institute of Traditional Architecture and Cultural Heritage, University Research Center, Tamnius. He is also a director of Computational Design and Digital Fabrication Research Lab, as well head of the School of Pedagogical and Technological Education. Professor Kyratsis received his PhD in CAD-based manufacturing process simulation from the Department of Production Engineering and Management, Technical University of Greece. He holds a diploma in mechanical engineering from Aristotle's University of Thessaloniki, Greece, and he received his MSc in Automotive Product Engineering and MSc in CAD/CAM from Cranfield University, UK. He has been involved in several industrial projects, and he has a great deal of expertise in both the design and the manufacturing aspects of product development. His main research interests include manufacturing, machining, CAD, CAM, and CAE system, computational design, artificial intelligence, additive manufacturing, CAD-based applications, product design, reverse engineering, and prototyping. He has published more than 20 books and more than 200 publications in scientific journals and international conferences. He acts as a member of the editorial board and reviewer to numerous scientific journals and holds 12 industrial design and 2 patents registered within the Greek Patent Office. With this brief introduction, I am now handovering the session to Professor Kyratsis. Sir, please.
Thank you very much. Let me. Hopefully you should be able to see my screen. So again, I would like to thank you for the invitation to be with you tonight and present the things that we are doing in our research laboratory here in Greece. And hopefully by the end of this presentation, some of you might be interested in collaborating with us. So the presentation today is CAD and CAE based simulation of micromachining and Industry 4.0 approach. And thank you very much for having all these pieces of information about my background. You have been very generous. The agenda of my today presentation is going to be, I'm going to discuss some things about our computational design and digital fabrication lab. I'm going to discuss about issues, pros and cons on CAD-based applications and 3D printing manufacturing, together with machining and FEA with the assistance of CAD-based applications. And somehow we are going to have all of these under the same roof. So as far as it concerns our laboratory here, we have a variety of hardware and equipment, and we deal with, we have a CNC machining, a 4-axis CNC machining from Haas. We do have a 4-component dynamometer that goes together with a CNC machining center in order to be able to measure F, X, F, Y, and FZ forces, together with the torque needed when we have some manufacturing process. We do measure surface roughness. Tensile, compression, and bending testing is among our facility. We have a variety of technologies for both 3D scanning and 3D printing. We have a laser engraving and cutting machine and a large format inkjet printer. Together with the hardware, we have a number of pieces of software, CAD, CAM, and CAE. Mainly, we are dealing with SolidWorks and Autodesk. And when we program this kind of piece of software, we use Visual Basic for application. We have the ANSYS mechanical suite for both linear and non-linear calculations. We use Deform 3D, which is a very unusual piece of software. You can see on the top side of the screen of this slide, I have some simulation results there. We use Deform 3D for simulating using nonlinear finite element analysis for machining. Either you can see some drilling in this case on the screen. We have ESCO for packaging design. We use Granta as our main software for material selection, GeoMagic for 3D scanning and the process of the data, Rhino 3D together with the Grasshopper in order. I'm going to show you some of the things that we are doing with this kind of CAD and API used, and further CAD systems like SketchUp and so on. So I will start now with the implementation of CAD-based application programming interface, the API, which when we use it in the design and manufacturing is a relatively new topic. So the API provides the user with a vast possibilities, and you can have a number of productivity enhancements. In general, programming with the API is in order to develop and customize software tools. And what can we do with all these software tools that we are going to customize? And I'm going to show you some of them. First of all, we automate the operation of various CAD features. Instead of actually clicking every time in the series of features or a series of commands on the CAD, we are able to do everything automatically. And then we are able to create different software modules and make them interact to themselves, or to communicate with different machines via the programmable kind of code. And I would say that generally we use it in order to be able to accommodate a number of engineering calculations. It sounds very good to use this kind of technology in such a way in programming the CAD system. And of course, we have a number of advantages, like we enhance the productivity of the designer and the manufacturing engineer. We improve the work and time allocation. We have a quick and easy error recognition during the product design cycle. We reduce the product development time, and this time that we save, we can use it to something which is more productive from our point of view. We can better implement the design ideas that we have in mind and better handling the product development. So it sounds very good, and probably someone can argue, why don't everybody do that? Because out of all these advantages, we have a number of concerns. The first is it requires understanding of computer programming. And I would say that usually engineers, especially mechanical engineers or design engineers, they don't like programming. So this is some kind of difficulty that we face all the time. Another difficulty is that in some cases, the benefits are not worth the investment in time and resources. We can discuss that if you want later on about this issue, when it is worth or not. And the third disadvantage is that we have a lack of thorough training guides, tutorials, manuals, and so on. So in a number of CAD systems, the users, they cannot find the manuals or easy to comprehend materials, or sometimes you cannot find it all, and you can do it only directly from the help. So I have split my presentation in different sections. I would propose after the end of each section, you can have some time to ask me any questions that you might have, and then to go to the next one, because I'm going to change the subject and the section quite a number of times. So at the beginning, I'm going to discuss about CAD-based design and manufacturing. We have a tool which we name it 3D Designer tool. The version that I'm going to tell you now, I'm going to present to you now, is a very simplified one, just to give you an idea how we use this kind of technology. And of course, we have the full version of this tool that we use it for a number of applications. So the main idea is to to create different modules that can be combined together in order to build a complete software tool, like the one that I'm going to show you, which is a CAD version of the Total one. So this tool is a general platform that can aid the design engineers to face the routine design tasks that occur during the product development. And in doing that, we can facilitate time-consuming tasks and then use them in a more productive way. And it is possible to extend this functionality to cover a number of issues. You will see more about that. So there are different chapters of how we can use the 3D Designer software tool. I'm going to start with a simple one, like if you go to one of the tabs, and one of the things that the tool is doing is fully automatically or manually, you can select using the topology issues, topological names of the object. And then by doing that, we can actually apply a feature of the CAD software. Let's say that for the sake of the argument, you can paint, let's say, one face. So automatically you can select a face and then you can paint it. There is not something really big about that, but the selection can be a hard procedure sometime in some of the CAD softwares that they are available. And then after we somehow select this kind of instances, then we can automatically generate different entities like chamfers, fillets, create some holes, and so on. In this case, you can put a number of parameters here and automatically have the output on the model that you create. Like in this case, we can create some fillets and chamfers, or we can put some extra piece of information for opening holes. But what about if we would like to have something more unusual, something more peculiar, like the flange pattern tab that we have built over here? And in a number of cases, you need to build a flange and include over here the different parameters, or in even more cases, you need to follow some kind of an ISO standard or a standard that you would like to have, and you can select over here the size of the item or the size of the product, and then automatically the CAD is designing it for you. Something that is, I think, probably is the most important in this little presentation of the 3D Designer tool is to automatically create engineering drawings. And then you can select over here different formats and everything. But I have over here an example for you. You can see that we can have a complete engineering drawing either of a part. So the part gets all the views necessary and all the dimensions based on a specific standard. Or if we handle an assembly like what you see now on the screen, we can see the assembly here with the different numbers from the bill of material, and at the same time to have a complete engineering drawing of the assembly. Of course, we are able to do the same for each part automatically, and then having the sub-assembly or the assembly of the sub-assemblies all together and have a complete set of drawings, which are very crucial when you go to the shop floor. So if you would like to ask any questions before I go to section 2, I'm more than happy to answer. Or if you would like to continue with all the sections and to answer the questions at the end, I'm more than happy with that as well.
Hello, participant. Have you any question?
Yes. Okay. Maybe it was a relatively simple, this section. Let's go to the next one. What about if we would like to design something which is more peculiar, something more advanced, difficult, I don't know, somehow it's different. So in this case, we are able to program using textual or visual language. So in this case, I will go a bit quickly with that, but we can use visual programming, which means that on the screen we will have something like that. So we have different boxes with input and output, and inside each box we have some kind of a code. We use a number of libraries, and then we are able to build what we call spaghetti here, the whole software like that. Of course, we are able to use the textual language as well. In our case, in some of the systems, we use Visual Basic for application. In some others, you will see later on, we are using Python, again, because there are a number of libraries that are available, and it is very helpful. And then, because we are able to have the textual language, we are able over here to create a new box, a new kind of function or procedure, or an object, which is going to be used inside this spaghetti, but it's going to be made of ourselves, so depending on what is the application that we want to run. I will give you an example like over here. We have built a small script, which when you have a little object, whatever geometry, it is not relevant in this case, and you have a plane, and then you declare these two objects, then you can slice the geometry. We have been using Rhino 3D for this case study. We have written over here a script which is doing what I'm going to show you later on. And the main idea is that you can slice the geometry having different parameters over here, and you can see the alternatives in this case here on the right hand side of the screen. And then if you actually do all that, this is an application that we are using extensively, not only for this very simple geometry, but for high-level, very complex geometries, usually for the furniture industry. And then what do? You can get a CNC laser cutting or a CNC machining center to cut all these geometries and then assemble the final furniture if this is what you want. Another example would be if you have a surface like you see it over here, and you have plane A and plane B. You include, again, the code is written in Rhino 3D. There is some kind of a Python kind of code over here. And then what does it do? You give all these parameters as an input, and you have the output different every time. And depending on what is the one that is suitable for you, you keep it. And then for this case, again, usually we have different applications for products which are made of wood. You can use the CNC laser cutting technique or a CNC machining. And then if you will go to something a bit different, to use it, you have, let's say, a pattern over here. In this case, it's a very simple pattern. We create a visual code, again, using Rhino. We have, let's say, a simple geometry for the sake of the argument here. Depending on what is the pattern here, we can explore different functions of the size of this geometry, which is going to be repeated. And then at the end, you find yourself having different applications, different alternatives on the patterns. And of course, someone is going to argue, why do we use that? In our case, we use it for 3D printed plastic structures on textile. So we print this kind of alternative patterns on textile, and then you see that like that, we change the geometry and the mechanical properties of the textile itself. This is sometimes you can call it 4D printing, if you would like to have a quick search in the bibliography. Okay, this is section 2. Again, hopefully it was relatively easy. If there are any questions.
Yes, sir. One question what I can ask that computational design and textual programming can be used parallelly for making the object.
Actually, we have started some time ago by having the textual programming. And then we found out that by using the visual, we had a lot of code ready for us. So it was very easy to handle it. Instead of having a lot of lines in front of your screen, we had only a box that you can play with. And then we needed to have some extra functionality. So we end up with using visual programming to make it easy to see it on the screen, while at the same time we use the textual to create our own boxes of functionality. And like that, we are using both of them, both of these techniques, in order to optimize the time that we need in order to develop our application. So this was very good question, because we try to combine both of them. It's like a hybrid way to do it.
Sir, one more question is there, sir, in text
yes,
chat box.
Nowadays, the generative design steals the CAD platform. Is there any AI tools currently available to do this function based on our prompt? If you ask my students, they like using AI in order to help them when they program, especially using Python or C and so on. So from this point of view, we have a limited use of AI in order to give us a rough idea sometimes, if you don't know exactly how to sort out your problem, to give you a piece of code. Generally speaking, we don't actually use any AI tool at the moment, although it sounds very good. We haven't been playing with that so much. Okay, if there are no other questions, let's go to the next one, which hopefully is going to be a bit different. So there is some kind of a simulation using CAD-based techniques for the drilling manufacturing process. I have this little video, we will see it later on. We name this piece of software Drill 3D, and it's what we call CAD-based drilling simulation. I'll give you over here some kind of a entry or how it works. You see over here we have a different data input. I will go through that, so I will skip it later on. So the first box over here that we need to fill are tool design parameters. So they are parameters that they have to do with the drill tool itself. And then over here we have a tool manufacturing parameters. We'll see there is a graph later on. Different distances in order to make it work like when the manufacturer is building the drilling tool itself. We are using the flute shape with this function. You can use different functions if you want, and we have the different cutting parameters. We feed all these data inside our software, and then it calculates the tool, and it calculates the work pieces. And as you see, maybe it's not very clear here, there is a little hole here, is the work piece number one, and the work piece number two, which is this little bit which is missing there. We'll see later on why do we do that. By doing all these things, and if we run the software, then we end up with a calculation of the total thrust force in each case for different tool diameters, for different feeds, for different web to diameter ratio, and so on, speeds and so on. So this is an alternative way, and someone hopefully is going to ask me, why do you use FEA and you use this technique? You have to ask me later at the end of this section about that. Let me make some comments about it. So the drilling is supposed to be very common material remove process. Even nowadays that we go from the metallic parts, we go to the composites. In order to somehow connect them, we need to do the drilling. So it's very important, even nowadays with the new materials that we use. Unfortunately, the tool geometry is very complex. And then in this case, which is a relatively simple case of drilling, we have to split the cutting process between the cutting process of the main cutting edges, the lips, which are these areas here, this one and this one. And then we have the chisel edge. The chisel edge is over here. It's on the kernel of the tool. And then we have the flute, which is over here. It's the area of the tool that the chip is going along in order to be removed away from the workpiece. Traditionally, Researchers, they have started with mathematical simulations or experimental simulations. So in our case, because we like programming in CAD software and we will use the API of a general purpose CAD system, you will see how we handle this kind of programs or this kind of problems. Hopefully, you will find our user-friendly environment, and then everything that we create during this simulation are solid models. Solid model for the tool, solid model for the workpiece, the anti-form chip, the cutting workpiece, everything is a solid model. This is not the case all the time. We can do similar stuff by working with lines or surfaces. But in our case, for the sake of this specific simulation, we have been using solid modeling. This is a graph which shows how does the drill tool is manufactured by the manufacturer, this specific twist drill. So what happens is we have these geometrical parameters, as I mentioned earlier on, and we have these manufacturing parameters. Because you need the grinding tool over here to cut this area in order to create the nose of the tool, then you need some distance on one side, the other, and so on. So we have to insert these, and one additional difficulty is all these are distances which can be found with some difficulty in the reference in the books. We have something like that on the screen. As you can see, we have the tool geometry and the manufacturing parameters. Over here, we have different values, how many steps should the simulation do, what is the step depth, and so on. In this case, we needed to run a lot of simulations until to optimize the number of the steps and the number and the millimeters of the depth. And the same is for the main cutting edges and of the chisel edge over here. And what should be the step in degrees of the rotation of the tool during the simulation. Of course, we need to put some cutting parameters like the feed and so on. We'll see later on this number of pieces is when we create the anti-form chip, we need to cut it into smaller pieces. Again, this is optimized values. You have to select in this menu what is the material of the tool, what is the material of the workpiece, and what is the speed that you are using. And then you can click either complete simulation and it works by itself all the time. It takes maybe 3 hours depending on the PC. Sometimes it can take 2 if you have a relatively fast computer and you have on optical you have a fast hard disk, or you can do it by clicking one step every time in order to be able to handle if it works properly, if there is any problem, at least to be able to spot where was the problem. So after you run this, then you can have, if you run a lot of cases, of course you need a little piece of software in order to read these cases. That's why we have this button, and then if you click this button, you come to this this kind of menu that it reads all the parameters introduced at the beginning. Over here you can see them, and then you click read results depending on where on the drive you are referring to, and the total thrust force calculated. And this total thrust force is calculated, as you can see over here, bit by bit by using 20 components of the cutting edge, or 8 in this case, because over here the length is very small in this case of the chisel edge. And then by summing these two numbers, you are able to see the total thrust force. And let's see a bit how it works. We put the input data as described earlier on. We have the calculation of the tool itself, and we have the work pieces, and we determine the kinematics of the drilling process. And then we penetrate we do the penetration of the tool inside the workpiece, and because it goes inside, then we have to apply a Boolean operation, which means that in the area that we have a common volume of both the tool and the workpiece, we can have what we call undeformed chip. And this happens for the main cutting edges or the chisel edge. I will concentrate a bit more. You can see over here the drilling tool, which goes inside the workpiece. There are a variety of parameters. When it goes inside, and after some time, in order to be able to achieve a steady state simulation, we are able to cut this undeformed chip, as you see it over here. And depending on what is the feed that we are using, you can have different variety of dimensions on the undeformed chip. This is for the simulation of the cutting lips penetration. Let's see now the little video, which is going to be more understandable for you, I suppose. You see, it penetrates inside the geometry, the tool, and then creates the hole. The same happens if we go to the chisel edge area, because this little cylinder that you saw earlier on, it's only for the chisel edge here to cut, and as it penetrates inside the geometry of the workpiece, then after we achieve the steady state simulation, we are able to see over here the undeformed chip. And why this is very important, you saw that over here, depending on the parameters, we have to optimize the degrees and so on, which this is probably, they are details for you at the moment. But I have prepared some videos over here. If you think about the undeformed chips, how they are removed from the workpiece, there is this little video. After the tool is penetrating inside the workpiece, this is what you subtract every time. And then the same is the case for the chisel edge area. And then we are able to automatically calculate the size of the chip, the undeformed chip. And you can see over here with the green, we have the chisel edge, and with the blue, we have the main cutting edges. And depending on the feed rate, we are able to calculate the chip width depending on the diameter or depending on the web thickness. And when we talk about the web thickness, is how big is the center, the kernel of the tool, and some manufacturers wanted these to be very thick, very wide, but in this case, you need higher force in order to apply for the drilling to happen. If it is very small, then there's a high possibility for the tool to break. So somehow over here, you need to do a compromise to have a web thickness which is thick enough to withstand the load, while at the same time, we have lower forces for creating the drilling, creating the hole. The same, we have the results for the half point angle, the nose of the tool, again, similar results, or the helix angle. If we change the helix angle, then we have a variety of geometries of the chip. And someone will argue, why do I need the chip? So now it's a surprise, because in order to be able to calculate the forces, to do the simulation, calculate the forces as you see them over here, we need to have the dimensions of the chip and then apply what we call the Kinsley model, the Kinsley formula. This Kinsley formula, is, I have it over here for you, for your reference. It has the dimensions, B and H are the dimensions of the cutting, the undeformed chip. And there are two coefficients, K and Z, which usually you find them into a database, and it relates to different aspects like material, manufacturing parameters, and so on. So in our case, we are going to find the dimensions B and H, while at the same time from the database, we can get the K and the Z in order to find what is the force. And then to be able to find over here, what are the forces on the lips here and there, and what is the force over here on the chisel edge. So after we have these, you see that we have cut them into pieces, and we calculate the different B and H every time, and then finding the Fi thrust of this little specific undeformed chip. If we go up to the end, we will be able to calculate all the thrust forces here and then sum them together over here. And because we have two cutting edges, in this case we have to multiply it by 2. The same happens in the middle. I told you that over here we have optimized it with 20 pieces to cut the part into 20 pieces. In this case, we cut it into to 8 pieces, as you can see it over here, because the geometry is far more complicated over here in the middle. But again, we are able to calculate the force on the chisel edge and the force on the cutting edge, and then to calculate the complete force over here, depending on the parameters used, like 12 millimeters diameter, the web, the ankle, the helix, and so on. So this is the end of this section. Hopefully this was a bit more unusual for you. If you have any questions, you have to ask me why do I use CAD-based simulation instead of finite elements. Okay, the simulation, the CAD system that we produced, the Drill 3D, was part of the inventor of Autodesk. So we program it in Visual Basic for application of inventor. For the composite materials, as long as we have this database, as I said, we have to apply the Kinsley formula. As long as we can find this kind of values into the database, we can do it. The Kinsley at this stage, usually they use metallic parts, like different metallic parts. Nowadays, yes.
Just I have also one question. Sir, when we make this simulation, in that during the modeling of twist drill geometry,
modeling, I'm sorry, the
twist drill geometry, are we considering the reduction on the flute length? Because that affects on the generator of chip friction between the chip and the flute surface.
Yes, actually, in this case, you can we don't do that, because of course there is some friction when the chip goes inside the flute in order to be removed, and this can be a problem and maybe can change the results if we have what we call deep drilling. In general cases, when the hole is not very deep, then there is no problem with that, because the friction is relatively small compared to the value of the thrust force developed by the tool. And I would say that especially because we have the chisel edge, I think it's 70% of the total thrust force comes from the chisel edge. That's why I said that usually we want this to be small, the kernel of the tool, but on the other hand, it may break. So 70% comes from the chisel edge, and only 30%, if I remember correctly, comes from the main edges. So in this case, the main factor of creating the thrust force is the chisel edge.
Okay, so in this software, basically we consider the lip angle area for simulation.
Yes, because these are the geometrical parameters needed for simulating the tool. At the same time, the difficulty, as I mentioned earlier on, was to find the manufacturing parameters. In this case, usually the manufacturers, they don't give you these values, how they make the tools. And nowadays that they make it with 5-axis CNC machining, they don't actually provide this kind of piece of information. You can find some of these values if you go back to the researchers that they used to do everything mathematically. So at the time they were spotting everything mathematically, And by transferring this data to solid modeling, then you can identify these kind of parameters. It is a bit of hard work to do it. I agree with you, Professor. And it is something that it puzzled us a lot. The manufacturers don't want to give us this piece of information. On the other hand, we need to have these manufacturing parameters. To be honest, sometimes we 3D scan the tool and try to with trial and error. So we have tried a number of techniques in order to identify this kind of parameters. Very good question, Professor.
Thank you very much, sir. Thank you.
So if there are no other questions, let's go to the next our next section.
Okay, we can shift on next section, sir.
Yes.
If there is no question.
Yes. So let's go to section 4. In this case, probably this is something that all my colleagues and my students, they like, 3D printing. So what we try to do nowadays is try to study the 3D printing properties. And we have been using for this case study that I'm going to present you today, the ABS, which is it's an ordinary piece of material using an FFF printer, and try to see the structural characteristics of the geometry. Let's see how it works. So we have been using ABS, and in order to study it and to make the model of it, we use a shallow neural network. So again, over here, we come to the CAE in a different way. Someone would expect to see finite elements only, but again, this is a different CAE way of modeling. And the whole goal over here is to be able to investigate 4 structural parameters on the generated S to M ratio. And what do we mean with S to M ratio? Usually, if you search the topics of this area, you will find that people, they do the testing of tensile testing and getting the strength. In our case, what we did the ratio of strength divided by the mass of the item, because apart from having the manufacturing parameters for high strength, at the same time, sometimes we need to have the lower mass possible with a higher strength. So you see that these two results, they contradict to each other, and this is very interesting. That's why we got this S to M ratio. We use the design of experiments technique, and for this we use the central composite design. We had 4 structural characteristics, and for each characteristic we had 3 levels. By following this CCD algorithm, we needed to perform 31 tests. And in order to be able to see that we don't have any problems with the testing, we applied twice for each test was measured twice in order to be able to see that the result that we get in the testing appears well both times. What we did, we have all the specimens over here. We'll see later on that we measure the weight of each specimen, and then we had this tensile testing by doing the tensile test. And then we study the workflow. We have all this neural network modeling with having this hidden layer. Over here, we have the structural parameters. We have the 4 structural parameters. We'll see them later on as well. And we have 3 levels to each. And we have over here the fabrication parameters that we use, what we call the constant fabrication parameters. And these are the structural parameters that we were changing. And then the specimen had a geometry follow the specific standard for the dimensions. And then you can see here the different values of the layer. We have a 0.1 of the millimeter, 0.2 and 0.3, and how this appears on the screen when we create the model and the code to be manufactured on the 3D printing machine. We have the infill. We have the 20%, 50%, and 80%. And you can see over here the difference on the geometry which was built before testing. Then we have the line direction. we have the 0, which means that along the testing specimen, we had this printing like that, or the 45 degrees, or the 90 degrees. I will tell you the results later on, but it's obvious that someone would expect this to be stronger and this to be the stronger, the second stronger, and this to be the last stronger in this case. And then we have different patterns. We have tried grid, triangles, and honeycomb as a different pattern structure selection. And then we use the 3D printer that we have in our laboratory here, the CreateBot D600 Pro. Of course, it's a very big printer. We can print items to up to 600 millimeters by 600 millimeters by 600 millimeters, so it's quite big. But in our case, we just print only the specimens. You can see over here after the fabrication and the numbering of the specimens. And then the testing machine here. We went through all the tests. We used an Instron 3345 universal testing machine. And in this case, we have been using the 5 kilonewton cell because of the values that we received for the testing. And then some trials over here. As I said earlier on, we measure the weight of its specimen with a very high accuracy. And then we have built a neural network. We decided which one was best compared to the R value over here. We select this one, and then we build the neural network. We did some normalization of data. I'm going to skip all this. We create the function. Each function has some coefficients. You can see them over here. I'm sorry. And then we did the network evaluation for the training, the validation, and everything. Everything went really well. We have over here the main effect plot. I'm going to show you on the next slides what are the results. But you can see over here that we have a very steep increase in this case. Over here, with the percentage of the infill, we have a lower value over here, and then it becomes constant. And this one is decreasing and so on. So we'll see later on the results. And then we can see the comparison between the predicted and the experimental results received from the neural network methodology. And all this of the S divided by M ratio, so the strength divided by the mass. So the conclusions in this case is that the layer thickness is the most influencing factor. We saw that on the graphs earlier. The direction of fracturing is feature affected directly by the line direction. You would expect that, as I said earlier on, with when I was presenting the parameters, which means that 0 degrees is responsible for higher S to M values. And then the influence patterns produced by the density indicates that both 50 and 80% have almost the same influence. You saw it over here. And then the general conclusion is 20% density contributes towards the achievement of higher S to M values. The honeycomb was determined to be one of the yielding the highest possible S to M ratio. And finally, the results of the neural network model was very accurate, up to 1% of difference. The error was very small, to up to 1%. I'm sorry. So if you have any questions now, I think we went to something which is a bit more fancy, a bit more, I don't know, what you would expect me to say in this presentation. If you have any questions, or you saw the finite element that you want me to go further with that. we haven't tried to compare different design of experiment methods, but it seems like up to now, every time we have been using different methodologies, it seems like we achieve very good results. But maybe this would be a very nice opportunity for us to check the comparison between with the same results, the same experimental results, to check the different design of experiment methodologies. It's a very good idea. I'm sorry, we haven't checked it, but it's a very good idea for future work. Okay, probably there are no other questions. Okay, let's go. Okay, it's something which is a bit more fancy, but it's more difficult. Let's see how do we connect CAD-based programming with nonlinear finite element machining. Okay. This is the layout of an application that we have built based on a specific standard for turning inserts. And then you will see later on how we can change all these parameters to create different inserts. So in this case, we use different geometric parameters for creating turning inserts. This is an insert. If you go over here and you actually zoom in, you will see that there are some chamfer width and some chamfer angle. And then we can use that. Again, we have different geometries. These are more micro geometries, and these are more general geometries, angles, and so on. And what we have done is we use SolidWorks API, which is mainly a VBA kind of application. And then in order to parametrically design the turning inserts. And these turning inserts were based on this specific, over here, as you see over here, standard. And when you have this application here, there are a lot of buttons to press, but generally speaking, what we do is we have to select over here what kind of shape and length we would like, what is the thickness, the nose radius, the clearance, the clamping system, and so on. We have over here some cutting edges and so on. There are different variety of inputs that we need to put, and you can see over here all the variation, the alternatives that we can select in order to produce a specific turning insert. And of course, we can save it in different formats. In a number of cases, we prefer to have it as an STL. And then we can over here say where to be saved in order to find it. And then you can just click Design Insert and you have it. And you have over here the code, over here with the colors. Let's see a little video, how it works. So you see, as long as you find the correct parameters, you can change that, and in just few seconds, you have the model of the insert. So, okay, we have these FEA-ready turning tool models or applications that create this kind of FEA-ready turning tool models. And then what do we do with these models? In our case, what we do is we import them into Deform 3D. This is a piece of software that I told you earlier on. You can Google it. It's very impressive to have this kind of software. We have been using that for a number of years, and it's quite accurate. It needs a lot of experience in achieving accurate results. But at the end of the day, we can actually generate FEA models based on the parts that we design with the application that you saw earlier on. So the result is something like that if you use it for turning. So again, turning is one of the most common machining processes used to produce parts, especially axisymmetric parts in the industrial sector. Accurate prediction of the generated machining forces is a key factor that can lead to cost reduction. Not only cost, but at the same time to have a better quality of the surface produced. And in order to achieve the aforementioned tasks, the implementation of finite element methods and similar techniques are widely applied. And this is what we're going to do. So we can follow two paths to have a 2D analysis, which is usually very good when we have some analytical rigid parts, and we can reduce the calculation time. It simplifies the mechanical problem and is ideal for preliminary simulations. In our case, usually we go for the 3D analysis, although in a number of occasions we have done a lot of 2D analysis in order to find some parameters that we need for the material. But generally speaking, we would prefer to have the 3D analysis, which produces results closer to the real condition of the cost of the computational time. It uses the full geometry of a tool and is ideal for complicated simulations, especially when we go to all these machining kind of processes. In our case, I'm going to show you some turning process. You can see that we have a specific tool holder, while at the same time over here we are positioning the insert designed as I showed to you earlier on. And then in this case we can have another piece of insert, and again the holder. We can keep the same holder in this case if we have the same insert, or change it. You will see later on. In our case, we have a cylindrical workpiece with a diameter of 72 millimeters, and we can calculate, or our aim is to calculate different forces. And as you will see over here, we have different tools and different holders. Generally speaking, we'll see that this tool is a square and this one is rhombic. And we will try to compare using one or the other, or what is the advantage and so on. But the main idea that is that at the end, what I would like to have is to calculate the force, the main force, the resultant cutting force, which comes from this formula, as you know over here, for the FT, F-arc, and the FA, the tangential, the radial, and the feed force component. So in this case, you will see that we have this rhombic tool. We have all the dimensions. This is a no-coating tool, ceramic, and it is designed to deal with standard grade for steel and cast iron. And these are the dimensions as you see them over here, following a specific standard. There's a similar geometry over here with a lot of details, these micro details over here, about the square tool. And then we have the different tool holders. And let's go to the workpiece specifications. It's an arc-shaped part of cylinder. You will see on the next slide what I mean part of a cylinder. The material is the one that was specified over here. The cylinder diameter is, again, as I said earlier on, 72 millimeters. But this is the one that we are using. But if you see macroscopically, this would be the working piece that I would like to have. But instead of having all this, and then at the end of the day, the tool is going to cut only in this area, instead of messing the whole geometry, I'm getting this little yellow part having it over here, and actually cut, using the finite elements method, this area over here, and then see the results instead of actually messing the whole this very big geometry, which is not going to be used during the cutting process. And in this case here, you can see how we develop the chip, in this case and the other case, together with the forces. You can actually spot the different meshing. I will give this detail here as well, because I think it's more pictorial to see. You can see over here we have meshed this area, and in this specific software that we use, the Deform 3D, we are using this 7:1 mesh size ratio. You can run the software with different mesh size ratios as well, but we have found that if you take all these little tips, then you can have very accurate results at the end. So we have followed, and that's why I'm saying that we have this 7:1 mesh size ratio for the working piece, and the 4:1 mesh size ratio for both the models for the cutting edge. Again, over here you see that we have the depth is 0.4. I'm going to mention it later on. In this case, we have the specifications like the rigid tool meshed with approximately 50,000 tetrahedral elements. The finer mesh, the tool nose having this 4:1 size ratio. We have plastic workpiece, arc-shaped, and it's part of the cylinder of with a diameter of 72 millimeters. Varying mesh according to the value of the feed. The finer mesh 7:1 is for the section of the workpiece where the contact with the tool is in effect. So concentrate over there with this finer mesh size ratio. The workpiece material is the one that was specified. The tool model is again the one which is specified, and the main idea here is for the microgeometry is that the nose radius is 0.8 of a millimeter. The cutting speed 75 millimeters per minute, 110, 140. The feed 0.12 millimeter per rev, 0.16 and 0.20. And the depth of cut, as I showed you earlier on, 0.4 of a millimeter. We have used the Johnson-Cook model, the generalized Johnson-Cook model, and the normalized Cookcroft-Latham. We have the constitutional model over here with different parameters. These are the properties for the material itself. And this is the friction modeling, which for our own case was we set up the 0.6 in this case, although we can change it depending on the result that we get every time, depending on the lubrication and so on. What about the boundary conditions? The workpiece was fixed in such a way so that the velocity of the nodes for X and Z axis was equal to 0. The tool was allowed to follow the path. You would expect that, this angular part, this cylindrical path, as I showed you earlier on. Something which is very important is the heat exchange with the environment. So the boundary conditions were assigned to all the surfaces of the workpiece. So all of them, they were exchanging heat with the environment. And the master-slave contact relationship was set to the workpiece and the generated chips. So I'm going to show you first what is the simulation. You see the different steps every time of both the tools, the rhombic and the square, and you see the different steps. For those that they are a bit unfamiliar with that, each step is running the model, the FEA model, again and again by changing the geometry. And again, usually when you use finite elements, linear finite elements, it means that apart from the rest, the geometry has a relatively small changes. In this case, that we produce the chip, you see that we have a very large deformation. That's why the piece of software needs to stop regenerate the mesh based on the new geometry, which changed, and then again remesh and solve the problem. So someone would expect over here that 2,000 times the model was remeshed and resolved again and again in order to produce this simulation. I have saved some of the images over here, depending on the tool that we are using, different steps all the time, and you can actually see what you saw earlier on the video on the moving simulation. You can see over here how the chip is developed on the different steps of the simulation. So you see the chip morphology. In our case, usually we do the same the same experiment in our own machinery here, and then we see that it's exactly the same, or we get the feeling of it. And then if you see over here, what are the forces calculated in each case, you can see over here one tool and the other tool, depending on the test. And you can see the FR, the FT, and the FA, and you can see on the lower right hand side the resultant force in each case. And then because we had activated the calculation of the temperature, as I said earlier on, it was one of the issues that we would like to study. We applied boundary conditions for heat transfer, so we were able to calculate the temperature in each case, and you can see on the left hand and the right one the different tools. You see with the red is the higher temperature, and you see on the histogram, the values of the temperature in degrees of Celsius. Again, lots of steps, 2,000 steps in this case again, and you could actually see how the chip was removed. And again, over here we have some pictures of the simulation in the different steps with the temperatures for this step, depending on the velocity and so on. And then that's why we have some results, some conclusions, like the radial force is the component that affects most the resultant cutting force for both tools. The developed machining forces are higher when using squares inserts. So by comparing all these, this is some kind of the result, the outcome of it, with the exceptions of the feed force, which is about the same for both cases. Increasing cutting speed decreases the percentage of increase, whereas the same effect applies with a feed increase. The temperature distribution seems to be spread to a larger surface when rhombic tools are used. And finally, both rhombic and square inserts produce approximately the same temperatures when we have identically cutting conditions. So, any questions? We have published a book. Oh, very big one. What would be the minimum size element you are speaking about? The concept of nano machining, the cutting parameters are set in a nano range. For the free holds good in this aspect. Okay. I would say that in our case, the nano, it is out of what we are doing. It would be a very good idea to start playing with mess-free FEA tools. We haven't done it up to now. We have put a lot of effort in using Deform 3D because it's one of the tools that it took us quite a lot of resources from our laboratory. I mean, it was relatively expensive to buy it and to maintain the license. So we try to make the best use of it. So from this point of view, we haven't tried this mess-free FEA approach, which would be very interesting, I suppose. I have seen in the literature some results that they seem to be accurate enough, but I don't have any experience in doing that. For the coolant, again, as I mentioned earlier on, we are able to create some boundary conditions about the area, the outside area of the model. So depending on what is the coolant conditions, we can change this kind of these values in order to have different conditions for the coolant. And the best question, I think this is Maches. I suppose the first is the first name. Maches is very good questions. How do we validate the FEA results? Every time you some journals they send me papers to review. This is the main thing. How can we validate the FEA results? From our own point of view, because we have a dynamometer, when we actually run the simulation, we are able to first to run the experiments, and then we do the FEA analysis. Some of my colleagues, sometimes they do the opposite. I would prefer first to do the experiments and then try to figure out how to run an FEA analysis to be able to manage to validate the results. So we do it, I think we do it the correct way, but I know that a lot of researchers, they do it the other way around. So we validate the FEA results only with experiments. Give approximately the same temperature. Is there effect of aerobic angles versus? We have to do probably more calculation, more simulations about that. And to be honest, I like that. There is a trick that I'm going to tell you now. There is a trick. Is the fact that I showed you some models of turning. Someone will argue it was very impressive. It is. I prefer drilling, milling, and so on. But in order to run, let's say, 30 or 40 simulations for turning, it makes sense. We need maybe 1 or 2 days per correct experimental simulation in turning. If you go to, let's say, drilling, probably you need a week, even sometimes more. So for 30 experiments drilling, even if you set up the model correctly, you need 6 months, even sometimes even more, to do all the simulation work. So I would prefer to do some drilling because I like it. This was part of my PhD anyway, so I like drilling more. But from the finite elements point of view, it is very intensive to use it for simulations. So if there are no other questions, let me go to the next one. Okay, which probably is going to be a bit more for all these people that they like CAD, is going to be closer to what they would expect from me to present today. So now you know that we have an application that creates inserts, and you see this little insert over here. And since we have that, we have done the first, let's say, step in order to do some CAD-based simulation. And in this case, what we do is we can have this insert, especially if we have a holder as well. So I'm not going to argue a lot of that, but you position this insert over here. You have the model for turning, and what do? You insert over here a number of parameters, and by moving the insert around, you can actually apply Boolean operations and subtract the area that the insert touches the cylinder. And by doing all that, then at the end of the day, you end up with the roughness. How is this possible to get the roughness? I'm going to show you here. Let's say that we have this little bit of the cylinder, and then we have the tool over here. And then what do? We do the tool, move the tool around, and then start subtracting the geometry from the area over here, from the area of the turning of the cylinder by doing the turning. And you see over here what is the profile that you will get at the end, and you can see the topography over here as well, and you can measure different parameters for surface roughness. And you do that on the CAD system by subtracting the geometry of the tool, in this case of the insert, from the workpiece over here. And then by doing that, as you can see, you get at the end this kind of geometry, and then you have all these measurements, and you can over here save it at the end to have all these values saved on a text file. As you will see over here, you can do that in a variety of different inserts. So as long as you have the program to create the inserts, and then you have the program to move the insert around the cylinder, which we are not actually, as you saw earlier on, we are not using a cylinder, but only a piece of it, as you see it over here. We are able to combine both applications, CAD-based applications, in order to be able to solve the roughness. And then, because I'm going to have the same question later on, how do you verify what you have found? We are going through creating samples experimentally. We cut some samples and then we measure them. As you see over here, how we create the samples, and then over here measuring them and getting the values. And then at the end of the day, you can see for the RA, RZ, RT, what do we get? We get very good correlation between simulated and experimental results. And in addition, if you see actually the graph, what is the model compared to what you measure using the Stiliscus piece of equipment, then you see that these are quite well positioned, one on top of the other. And then if you go to the microgeometry, you can see over here the tool, depending on what is the nose, if we want the standard nose or the wiper and so on, depending on exactly what do you use, you come over here and you have at the end a different topography. Like if you use a wiper nose radius, you see over here the topography is quite different. But again, this is part of making the CAD system and all these Boolean operations which are necessary working for us, I mean, in order to do all the maths. So an alternative way to calculate the surface roughness using a CAD piece of software. Any questions on that? Okay, I had prepared the presentation up to here for what you would expect me to show you, but I have more chapters because I see that we have 10 more minutes. If you want to go through something which is more close to 3D printing applications and how do we use CAD-based programming for 3D printing, we can go through another application, or if you would like to stop because it's the time passed, I'm more than happy to stop. Professor Tyler. Okay, let's go for one more section then.
Sir,
So
there
you
is
saw
a
the
one question in chat box. Professor Pan, there is a one
okay, I'm
question in
sorry,
the
I'm
chat
sorry.
box.
Yes, I'm sorry. Okay, in this case, again, it's a very good question, and I really appreciate your question. What we usually try is to use tools, not excessively. So for every experiment that we use different tool, which means that we have a lot of tools or a lot of inserts. And we are doing that exactly because you imply that, because when we have a wear, then all the values of the radius of the tool and so on, they are different. And of course, if they are different, then even the surface produced is different. So I totally agree with you that we need to have in all the experiments to have a completely new tool. And this is something, sometimes it's expensive for using the inserts is not a big deal so much because we can find them relatively with a low cost. But if you go to bigger tools, then it can be a challenging problem. Thank you very much for your question. So if you are curious, I can go to the next section. If you are not, I can stop here.
Yeah, we have 5 to 10 minutes.
Okay, let's go
Still.
to that's why I have created another section.
Yeah.
Probably it's going to be more, I don't know, maybe more fancy. Usually my students like this kind of stuff more than what I like. So let's see how we can use CAD-based design and manufacturing for, in this case, for slipper modeling and prototyping. So the problem that we have is to create an algorithm in order to automate completely the design of a pair of slippers. And for doing that, we need two sets of data. One is to scan a 3D, to have a 3D scan of a foot, my own foot or my students or a foot. And then we need the plantar pressure exerted by the foot on the ground when the user is standing on top of it. And then we are able to 3D print these solutions. I will skip the details, but the main idea is to be able to somehow write a piece of code that creates geometry. You see the geometry here, how it works in 2D, but later on I'm going to show you the 3D application of that. By having different structures, we are able to insert the different geometries inside the space, the 2D space in this case, and to repeat this, this shape again and again, and then try to deform this geometry. Although it looks very easy to do that in 2D, we'll see later on when we go to the 3D, then it becomes more peculiar to have a 3D structure, which is going to be used later on, and so on. I will skip the details of the geometries. I will show you how it works. So I have over here the pressure, how do I stand, and what is the plantar pressure map used for the user. And then by having these from the doctor or from the machine, then we are able to read it, to recognize the areas, to find which are the coordinate points of the high stress, and then create this geometry. And then by having this geometry, usually this geometry is not stressed, or let's say homogeneously is surrounding the whole. We don't have any how to name it. We don't have any deformation. But somehow we need to deform it, depending on, over here we have a high pressure, we need to deform it and have more material here and less material here that we don't have any pressure. And this is what we are trying to do. In this case, we have the initial mesh, having the three geometries as I showed you earlier on, and the deformed mesh, depending on where exactly the user had the high pressure on the slipper. As you can see over here, we have the foot, we have the slipper over here, which is designed. So apart from having the different deformations because of the high pressure, we need to have the feet of the user. And this is what we are doing. We scan the foot, and apart from having the initial shape, having the second with the auxiliary shape, this sandwich kind of geometry, we have the scan foot. So over here you can see that this is dedicated for this specific user. And then we are producing the geometry here, not only by filling the initial mesh, but by having the deformed mesh, depending on the map that we got with the higher the higher stress for its user. And we have produced these three shapes, different shapes, which belong only to the user that we have scanned the foot and we have got the plantar map. And then by having this printed on our 3D printer using TPU, we gave it to the user and say, okay, would you prefer this one or the other? And for this, we have different questions for standing position, normal walking, fast walking, and so on. We have different criteria of comfort, stability, pressure uniformity, and the final result. So at the end of the day, you could see that this shape had more points depending on the comfort, stability, and pressure uniformity. And this is the result. I'm going to skip it for now, the details. So you saw that at the end of the day, we can use this programming interface of the CAD in order to create geometries which are packed inside the product. Like in this case, we had the slippers and the bottom of the slipper, and increase the easiness of using the product, depending on developing this kind of applications. And again, this is a CAD-based application, which is based on visual programming together with some textual programming, which has been incorporated. If you have any questions about that, this was something like a little gift, some extra chapters, just to be on the safe side that you will find something interesting. I would like to thank you all for your presence here.
Okay, dear participant, good night.